So this lesson should be an extension of what you knew from Algebra 2, and we did worksheet 9A together a few days ago. I asked you guys to complete worksheet 11B for homework. That was very much a review from Algebra 2, but we're on worksheet 8A and 8B today for our lesson. We're going to be solving both logarithmic and exponential equations, but because it's pre-calc, we're going to have some more exciting problems than what you saw in Algebra 2. So, the first property we're going to explore is called the one-to-one property. And it's basically a common sense math statement. So like if something equals something, but they look really similar, then the stuff inside the functions have to be equal. So like for instance, this is an exponential one-to-one property. If it's the same base and they equal each other, well that means their powers have to equal each other. So for a lot of kids, they just look at this statement when we see the question in a second and they say, oh, I just set the powers equal to each other. That is absolutely true and accurate, and that's an easy way to solve the equation. You're not going to have to use a logarithm trick to solve this if you notice there's a one-to-one property. This first question here, in my Algebra 2 class, I called this the baby base method. That might be too immature for you guys, but if you could rewrite these as the same base, then you can equate their powers. So I look at my current bases, which are a 4 and a 16, and they do have a couple of different common bases. You could write them both as base 4. You can even go back and rewrite them as base 2. So I think for most kids, the easiest way to rewrite this is to say, okay, I'm going to rewrite 16 as a 4 squared. But remember, it's being raised to the x power. And then over here, you already have a base of 4, and it's being raised to the x minus 1 power. So now you got to use your properties of exponents from Algebra 2. And it says when you have a power raised to another power, the way you combine them is you multiply them together. So what you really have in this question is 4 to the x minus 1 power equals 4 to the 2x power. It's probably already done for you, isn't it? Here I am walking through it. Oh well. Now that we have the same baby bases, that means if 4 to something equals 4 to something else, the only way for this to happen is if the powers equal each other. So x minus 1 is the same thing as 2x. So let's see, that means subtract x over, you have negative 1 equals x. And for exponentials, you don't have to worry about extraneous solutions. There's your solution. So the example after that, again, it's already done for you. Oops, there we go. Or not. Oh, it is done. Okay, I'm going to warn you, this one's kind of nasty. It is not an Algebra 2 question at all. And maybe in honors you saw something like this, but probably not, actually, now that I think about it. You have an exponential equation. And it looks like a distant cousin to a quadratic equation, doesn't it? Like e to the 2x, and then in the middle term is e to the x. That's kind of strange. So what they would have you do is called U substitution. When something is trying to emulate a quadratic trinomial, that means instead of whatever the weird thing is, you could substitute it for u. So like in the middle term here, you have 3 of somethings, that's what u is. So you would say u is e to the x. So if I go back here, this is a little confusing guys, but think of it this way. This is just like e to the x being squared. So if we're substituting u for e to the x, that means this is really u squared. This is called u substitution. It's a weird little math trick. And then you have minus 3 times we decided e to the x is really a u. And then plus 2. So now it looks a whole lot like a quadratic trinomial, and we'd factor it. So u squared would be u times u, and then the back factors would have to multiply to positive 2. So how about a negative 2 and a negative 1, because they also have to add up to negative 3. So here you're going to solve, you're going to get u equals 2 and u equals 1, but there's a problem. We're not actually solving for u, we're trying to solve for x. So I go back to the beginning of the problem and I say u is really e to the x, so swap those out. E to the x equals 2, and e to the x equals 1. Now I do have to use a logarithm because, well, maybe not on this one, but if I apply a natural log, right, that'll knock out an e, natural log to both sides. You end up with, these cancel, x equals whatever the natural log of 2 is, and here x equals the natural log of 1. So if you wanted approximated answers, this one you could type in your calculator, but natural log of 1 is just the number 0, so this one's easy because it's 0, And this one is whatever the natural log of 2 is, which I don't think I have written down. All right, so that was a very challenging pre-calc question, and I think there's at least one on your homework that's like that. So let's take a look at some. Oh, this one's still done for you. How boring. All right. So anyways, this example is done for you. It does not have a common base this time. I like the baby base method when you can utilize it, but you're not going to be able to figure out 3 to some power giving you a 19. That's not a common base they have between them. So you have to apply either a common log or a natural log, and if you remember my little spiel about which one I'm going to use, I'm pretty much always going to use natural log with the exception of anything that's base 10. So it's up to you. You can use a common log if you want, but that's like 3 letters and that's 2, so that's better. So the log, the whole point of it is that it brings the exponent down in front. So you have x times the natural log of 3 equals the natural log of 19. And remember, these are just gross numbers. Natural log of anything is usually just a really icky number. So we're going to divide both sides by whatever this natural log of 3 is. Can y'all do me a favor, though, and practice on your calculator how you type this in? It's the natural log of 19, close the logarithm, divided by the natural log of 3. And make sure that you're always following instructions on where to round. They want 100th this time. So you should get, apparently, 2.68. Now, I notice in your notes, it does, you know, that's the notes question that's already done for you. They used common log, like a fool. But you end up with the same answer because the ratio of the logarithms works out the same. All right, for part B, I don't care who you are, you're going to use natural logarithm because it's base E. But we're not ready to use logarithm yet because you need to isolate your base. So the first thing they did was they added the 6 over. So it equals 7. And again, E's not going to have a common base with anything with a 7. So you're going to apply the natural log this time. And you're going to see some cancellation between the natural log and base E. So the 8x plus 1 no longer has a base holding it up. It's just going to drop down. And then whatever the natural log of 7 is. Now you'll notice in your textbook, and pretty much in every upper level math textbook, when they work through a problem, they don't want to hit the calculator until they absolutely have to. So they'll either solve this like simultaneously on their calculator in multiple steps. What they don't want you to do is hit natural log of 7 and then write down a truncated decimal because already you're making your answer inaccurate. So you'll see a lot in your like student manuals when you go to college. They'll have like natural log of 7 minus 1 quantity divided by 8. That's totally accurate of how you're going to solve this. So you're going to notice they did that same thing here on your notes. They kept it natural log of 7 minus 1 divided by 8, and then it approximately comes out to 0.12. Now you guys know from your science classes that if your teacher says your final answer has to be rounded to the 100th and you want to truncate decimals along your work, you're usually pretty safe as long as you keep a bunch of decimals. So I think a few of you found that trick in science. Like if I keep 6 decimal places, my teacher will never know the difference. And that's usually true in math as well. The problem is when you work with logarithms, a little bit of decimal change makes a big difference. So be careful. All right, done for you. All right, here's finally one that's not done for us. So we have an exponential problem, and you have to kind of ask yourself, is this a good question for a common base or a baby base? So I have a 9 and I have a 3. Is there a common base in that question? Sure is. And the common base would be a 3. So you're going to rewrite a 9 as 3 squared. This one already has a base 3. And then we're going to use our exponent properties. 2 raised to the x power, we would combine those through multiplication. So this becomes 3 to the 2x equals 3 to the, already was 3x minus 4 power. So now that you have common bases, the only way for these to equate is if their exponents are the same. So the next thing you set up is that 2x is the same thing as 3x minus 4. And then we solve. So I think you end up with x equals 4. That time we didn't have to round to anything because it came out to an integer. All right, be careful on 2. The common base there's a bunch of answers you could give me, but the answer I don't want to hear is 1/4. 1/4 would not be an easy common base for that question because I would challenge you to come up with a way to change 1/8 to 1/4. That's, I mean, you could. It's very difficult though. So the rule in common bases, baby bases, go small. So for a lot of kids, they say, well, I could easily change this to a 1/2 because 1/2 to the second power is 1/4. And 1/2 to the third power is 1/8. But then you have to remember again, you already had existing exponents over here. All right, so be very careful here. And this is usually where kids, they kind of skip this next step. So they just write the exponents equal to each other because they kind of see the writing on the wall that, oh, the bases are going to be irrelevant in this question. That's okay. Maybe not for your notes, though. In your notes, I would still continue on keeping the base of 1/2. And then this first 1/2's new exponent, be careful, it's 2 times the quantity 2x minus 1. So your new exponent is actually a 4x minus 2. And then over here, this 1/2, his exponent is 3 times the quantity 11 minus x. So you have a 33 minus 3x. Now you would say, okay, great, I have the same base. So my next step is to say the exponents have to equal each other. Oh boy. All right, so we're going to add 3x over. We're going to add the 2 over. And we came up with a beautiful x equals 5. Surely wasn't the only way. Was anyone kind of eyeballing a different base? Was anyone thinking about making it a base 2? Yeah, that would work. If you used a base 2, then you would have had a negative exponent to deal with, which is not the end of the world at all. Some people just really do not enjoy looking at fractions, so the minute they can change it out for not a fraction, totally fine. Some of you weren't thinking very deeply about that question and probably didn't care what your base was. That's okay. All right, guys, let's look at number 3. Common base here. You got one fraction, one non-fraction. How you want to... I think I'll take her advice. Let's go with 2. Yeah. So we're going to change 4 to a 2 squared. And it already had... Is that a 3x minus 2? Can't read my own writing. Equals... So how are you going to change a 1/2 if we need to make it a base 2? That'd be 2 to the negative first power, but already has an exponent of 2x. So you're going to carefully combine your exponents here, remembering that you're multiplying them together through the exponent properties. What is that? 6x minus 4 equals 2 to the negative 2x. You guys took me very seriously when I said you weren't going to talk during this lesson, huh? All right, let's solve. So 6x minus 4 equals negative 2x. Oh boy, I don't know. Let's just subtract 6x over. Negative 4 equals negative 8x. Careful on your division. Don't pull an Abruzzo and do dyslexic division. This is divide by negative 8. So x ends up being 1/2. Oh boy, 4 is one of those nasty ones. Here we go. So your book suggests a little technology tip, which is very helpful. They graphed the function, and they're telling you once you solve this, is that the same? That's not the same question, is it? No. They're saying once you solve it to verify it on your calculator, but when you hit the trace key, like don't type whatever the decimal answer is, like type natural log of 5 or whatever you end up with at the end of this. We're going to have a natural log of something on at least one of these answers. All right, here we go, guys. This is trying to look like a quadratic trinomial, but it's not quite succeeding. So what I do is I look at the middle term, and that tells me what I should substitute out for u. So let's call it u is really e to the x power. So if I think about what's going on right here, you have a 2 in front as a coefficient. And then you have, it's like e to the x squared. So remember, e to the x is really u. So you have a 2 times u squared. Which isn't really that surprising once I realize this is going to end up being a quadratic trinomial. You'll notice that a lot, especially when we get to the trig units next semester. Anytime we do some substitution, whatever this middle term is u, and then this term is going to be whatever that is squared. So. All right, so then plus 12u minus 54. And then I want to think about all my algebraic techniques for solving a quadratic. My first thing I notice is that all these are divisible by 2, so let's knock that 2 out of there. So you end up with u squared plus 6u minus 27 equals 0. And then you got a pretty basic factoring question. How about u plus 9 and u minus 3? But be careful, guys, it's u equals negative 9. And u equals 3. So now you got to come back and say, okay, u is really e to the x. So this question really says e to the x equals negative 9. And it really says e to the x equals 3. So now I'm recognizing why this little technology tip off to the side. Well, that's not the same question, it doesn't look like. But it's only showing me that maybe there's only one answer. Let's talk about that. What happens when you go to apply the natural log to this first factor? Natural log of negative 9 is an undefined expression. Natural log wouldn't go out to negative 9. So this one's undefined, therefore it's not going to produce you any solutions. But this one produces you a lovely solution of whatever natural log of 3 is. So for me, I'm just going to leave it as x equals the natural log of 3 unless, oh, it does say round to the nearest hundredth. So then I'd go type it in. I never wrote it down on my key. I'm sure you guys can type just fine. All right, guys, let's look at number 5. 9 and 12. While they do have some common factors, I think the problem is we're not going to see any common bases, at least not any obvious ones. So this would be a good candidate for just applying logarithms to both sides. You have your choice, common log or natural log. And Abruzzo always goes no, she doesn't. Abruzzo always goes natural log unless it's a base 10, which these are not base 10s. So I'm going to apply the natural log to both sides. Nothing cancels, but what it does do is it brings that exponent down in front. So 2x is now being multiplied by the natural log of 9, which is some gross number. And it equals the natural log of 12, which is some other gross number. And then to solve for x here, guys, you got to do a few things for me. You got to divide by natural log of 9, and you also have to divide by a 2. You can do this in one step on your calculator. All right, divide by natural log of 9. Now, careful how you're typing this. Make sure you open and close the logarithms effectively. You also, whoops, 9. You also have to divide by a 2. So at some point in your math, also divide this by a 2. And you should get 0.565. Please try typing that, guys. For a lot of kids, they try to do it in one step, which would work if you type it like this. Natural log of 12 divided by, you either have to hit natural log of 9 divided by 2, all as separate division questions, or this part you could put in parentheses if you write it as a multiplication question. So decide how you want to write this part. Oh, not like that, though. That was bad. And the most important part there, guys, is that you've ever practiced typing it. This happens a lot in Algebra 2, doesn't it? Where, like, the whole class watches the teacher do it, and they're like, yeah, totally. And then they go to the test, and then none of them type it right. So don't be that kid. All right, this next one. We're not going to find a common base, but we are going to be able to use a logarithm, and it's a happy day for me because you're all going to have to use natural log unless you want to do more work. So we're going to first isolate our base of dividing by 2.4. This probably doesn't come out very nice. But if I was trying to keep as accurate of an answer as possible, I'd probably just leave it as a fraction, because my next step is going to be to apply the natural log. So this is whatever 9.3 divided by 2.4 is. You go to apply the natural log. The right side's beautiful, or sorry, no, the right side's ugly. The left side's beautiful. Natural log and e are going to knock each other out, so the x minus 6 drops down. I think we just kind of have to, if we're going to write down work, you're going to want to write a decimal. But what's your next step going to be? You're going to add 6 to whatever this ugly decimal is. So whatever this is, plus 6. And I got 7.35. Tell me if that's not right. So whatever natural log of 9.3 divided by 2.4 is, close that, and then add a 6. All right. A lot of kids think there's a common base here. I don't think there is. Like, you're not going to be able to write a 6 as a base 3. So this is just a case where you have to use a logarithm. Neither one is a common log or an e, so technically common log, natural log both work, but you know me, I'm going to use natural log. So bad news here though, guys. When you apply the natural log to both sides, you have existing exponents. They are both going to come down in front of their logarithm. They also both have variables in them. That kind of creates a challenge for you. So you have a 2x that is now being multiplied by the natural log of 3. And it equals the quantity x minus 1. You're going to need to put parentheses around that. Times the natural log of 6. Okay. So you got to kind of boil down to what are you looking at here. Natural log of 3 is some disgusting decimal. Natural log of 6 is some disgusting decimal. You have to work with them. At some point, you're going to need to isolate x's. So, I don't think now is a good time to divide terms around because you have x's on multiple sides of your equation. So for most kids, the easiest way to approach this question is to distribute the natural log of 6. And you know what? While we're at it, let's just go ahead and multiply this together as well. How about, since we're rounding to the 100th at the end of this problem, just give me like at least 4 decimal points, and we'll say good enough. I mean, it's not like a life or death science situation where, like, if we don't round right, someone's going to die. So let's just be okay with a kind of truncated answer. Can somebody type for me? Don't type an x, obviously, but what is 2 times the natural log of 3? I do not have this written down, so I'm going to need your help. Wait, I do have it written down. Is it 2.197? Oh, excellent. Can you give me one more decimal, though? 1972, thank you. And then if you distribute a natural log of 6 here, well, apparently that's 1.792. Wow, dyslexia. X minus 1.792. Are we okay on that rounding? Did I do that part right? Do I even have the right number? You shouldn't. Because look how horrible those numbers are for someone who's dyslexic, like a Bruzo. That's rough. Okay. We're going to be solving for x, obviously. So you're going to subtract 1.792x. Is that... Oh, you know what? I will not have the right answer here, so I need some help on the digits because I rounded off too far. 10, 17, 8... 1, no, I give up. I was trying to do some second grade subtraction. It wasn't going well. What is it? Thank you. And then equals negative 1.729. So divide both sides by 0.4052. Is it roughly negative 4.42? I don't even know anymore. See, in my work, I truncated too early, so I don't know. I might have had the wrong. Thanks for being a good sport typing for me. You're pointing at my work like I did something stupid. What did I do? This? This is negative. Is that what you're telling me? This one. Ah! See, did I not say dyslexia? So which one is it? Negative 192. Ah, good call. So, like I said, what's the answer? Is it negative? 4.422. Okay, so negative 4.42. Because it does say 100. Woof. It was arduous, wasn't it? So we just learned a valuable lesson. It's not awesome when you have to apply logarithms to both sides of the equation and you still have variables on both sides of the equation and you have distribution. The good news is you guys don't have to look numbers up in a chart, so at least there's that. All right, the next one's super boring. You just apply a natural log to both sides. Moving on. On the back. So those are all exponential equations. Now we got to talk about how do you solve logarithmic equations. So basically logarithms and exponentials are inverses of each other, which means their properties are going to have similarities. However, your approaches are going to be completely opposite. So it still has a one-to-one property of logarithms, and it's pretty boring, but I'm going to encourage you guys to always use the term exponentiate. So when you are solving a logarithm equation and you want to get rid of a logarithm function, You're going to create an exponential function through the art of exponentiation. So when I look at this question, which is probably already done for you, so that's super boring, they don't really show the exponentiation step. They kind of skipped over that part, but it's a base 5 logarithm. So what they're supposed to encourage you guys to do is to exponentiate with a 5 on both sides. So 5 to the log base 5 cancels, and then it's 5 to the 6th power. So that's where they're getting this step from right here. A lot of Algebra 2 teachers just teach them to magically transform into the other formula with no knowledge of why that's happening. I would rather you guys, because of the level we're at, understand that we're really exponentiating both sides. So let's do one that's not done for us. How about that? Is this one done? Oops, I'm going the wrong way in my notes. That would help. Number 9. That one's not done, right? Okay, so we're ready to exponentiate. Technically, this is a one-to-one problem, so you can probably just tell me what I need to set up. But just for funsies, what base is this logarithm? 10. So really what you need to think about doing is that you're exponentiating with a 10 on both sides. So 10 to the log base 10 and 10 to the log base 10 will cancel. And this is where you're going to get that one-to-one property where if log equals log, that means the inside stuff has to equal. So you do get x equals 4. And I will warn you, on logarithm equations, you do have to worry about extraneous solutions. Because remember, you cannot apply a logarithm to something negative, right? You can't do that because it's undefined at log of anything negative. I'm not saying x can't be negative, but I'm saying what's in the logarithm can't be negative. We got to watch out for that. Oh, 10's fun. You cannot exponentiate until you have a singular logarithm on each side and they are combined, and there's no 2 logs on one side. So you have to use your properties of logarithms to condense these back together. This becomes log base 12 of, you're supposed to multiply these together, so it's 2x, good. And it equals log base 12 of x plus 7. So either using the one-to-one property or understanding that you're exponentiating with a 12. That's a 12 over so. So the 12 to the log base 12s cancel, and then the 2x equals the x plus 7. So x equals 7. And before I commit to that answer, I should have gone back and double checked. If I plug in a 7 into any of the logarithms where x is, I just got to make sure I don't have a negative inside of the logarithm. So log 7 is fine. This is log of 14. That's fine. Blah. Okay. Isn't that fun looking? Okay. Well, we need to do this one because something cool happens in it. All right, let's condense these together. You have, what kind of a logarithm, by the way? Base 10, common log. Good. Oh, what are you supposed to do with these inside pieces, though? Oh, boy. All right. We got to FOIL these together, guys. So think about multiplying 16x plus 2 times the quantity 20x minus 2. All right, here we go. I'm going to need a bigger parenthesis. Okay, here we go. 320x squared. Yikes. Okay, this is a minus 32x. And a plus 40x. What did I just say? A minus 32 and a plus 40 says a plus 8x. Yep, and then a minus 4. I guess I didn't need that big of a parenthesis. I kind of overshot that. Now, good news, the other logarithm is just a singular logarithm. And it does have that one-to-one property like we had in the last few questions. But technically what you're doing is you're exponentiating with a 10. But let's just kind of skip the middleman here and say the blue parts equal each other. Now, I'm not real excited about this because it looks like we're going to have a quadratic. Boy. 319x squared plus 9x minus 2. Okay, so definitely a quadratic. You're going to move everything to one side. I'm going to subtract this guy over. Let's see, 1x squared. We're going to subtract 9x over, so minus x, and we're going to add 2 over, so minus 2. Well, that didn't work out nearly as terrible as I thought it would. All right, so this quadratic factors pretty nicely. X minus 2 times x plus 1. So after all that work, we solve our factors. We get x equals 2 and x equals negative 1, but we got to stop and think about this. If I were to go back to any of the original logarithms, if I were to plug in x equals 2, that one's going to be fine, because look what happens. You get like something positive, and definitely something positive. But what happens when you plug in a negative 1? You get 16 times negative 1 plus 2, which is negative 14. Can you apply the common log to a negative 14? No way, man. So that answer is extraneous. The only viable answer is x equals 2. All right, this next one, you have to condense. This is a very boring question. Okay, I'm bored of these. You condense them together, you multiply, and you solve. This is another one where it's a quadratic and one of the answers is bogus and you gotta cross it off. Okay, let's look at these story problems. This is where we're heading next week. So you're gonna be going back to all these story problems that you guys were able to solve on the calculator, and now I'm gonna be asking you to solve them by hand. So the amount of radium present after t years can be modeled by that equation, where a sub naught is the initial amount. How long will it take for 50 grams to decay to 10 grams? So remember, a sub naught is the initial amount. That would be the 50. So 10 grams is our final amount. And in our formula, the beginning of the formula is the final or current amount. So the 10 goes here, and it equals 50 times e to the negative 0.00043 t power. And your job is to solve for t. So this is an exponential equation. We're not going to have any common bases, obviously, because it's real life, and real life isn't nice like that. So you're going to isolate the e, and then we're going to apply a natural log, of course, on this question. So divide by 50 on both sides first. And it's not a terrible decimal, but you can just keep it as 1/5 if you want, but you can call it 0.2. Equals e to the negative 0.00043 t power. Now you have to apply a logarithm to bring the exponent down. Our suggestion is for you guys to apply a natural logarithm in this case in particular because of the natural log in e. So whatever the natural log of 0.2 is, I'm sure it's disgusting. You're still not done, because what you have right now is the natural log of 0.2 equals negative 0.00043 t power. So a final algebra step would be to divide by this negative 0.00043. But this is what your science teachers and eventually your upper level math teachers want to see. I would rather see this work down on your paper than somebody who immediately grabbed their calculator and gave me like weird truncated decimals along the way. So keep the natural log as long as you can, basically, in your work. What does this come out to, by the way? Should be a pretty substantial amount of time, guys. Like 3,742. Yeah, I wrote down 0.88. I just was in the habit of going to the hundredths place for some reason. I mean, it's quite a bit of years. I don't really know if that last hundredth of a year matters. So roughly 3,743 years. Hang tight. Good times. This is, I mean, not that question, but this is how they do carbon dating on your fossils, right? Fun. Any paleontologists out there? No? I don't really know if that's a thing anymore. Is that a paleontology? Like, is that a lucrative field? It's just for fun? I feel like there's not a lot of things left to, sorry, internet, just offended some paleontologists out there. I don't know. I feel like that's not a direction I would suggest you guys go in college. I feel like while that might be a cool, fun spring break trip, maybe not a career. Okay, you go ahead. He'll show up in his like Jurassic Park uniform. I dig up dino bones. Alright. I know I'm gonna get hate mail now. Oh, how do I edit videos? I gotta look into that next hour. Okay, Richter scale. Richter scale, that's where it's at, guys. Alright, so I'm just going to keep recording, and y'all want to see what happens on the Richter scale. My bulb just went out in my projector. That's paleontology. They're coming for me. They're like, make fun of my career, will ya? Alright, guys, so that formula is a little messy. Alright, the 6.0 is the magnitude of the earthquake. So that's what you have to put in place of the R for the Richter scale. So you start off your formula with 6.0, or 6, equals 0.67 times the common log of 0.37 times E, where E, oh, plus 1.46. E is the energy that it releases. So you're going to need to solve for E. Your first step is going to be to subtract 1.46. And already we got nasty decimals to work with, but whatever. Whoops. I got, what do I have? You know what? I have the wrong answer. Because I think I didn't have the 1.46 on my work when I keyed it the first time. Can someone tell me? Because you know I can't do this in my head. Thank you. 4.54 equals 0.67 times the common log of 0.37e. So you're still not isolated as far as logarithms go. So the next thing you need to do is divide by 0.67. Oh, I'm so sad. Someone get Isaac back in here. All right, 4.54 divided by 0.67. What is that? 6.7761. Thanks for all those decimals. And then you're going to exponentiate both sides with what base? Because this is a common log. So what base are you using here? A 10. All right, shove a 10 underneath both sides of the equation. Visualize it. All right, so on your calculator, make sure you're typing 10 to the 6.7761 power. Go ahead and rattle off some decimals for that one. I don't know. 597.727.749. Okay, and then you're going to divide that number by 0.37, and you get some gigantic number, which makes sense because it's the energy of the earthquake, so it's a lot. All right, bye.